Alright, so picking up back on part B, we had um, talked about how on this block, which was on the 41-degree ramp, and if you need to go back, go into the first video. In the first video, I showed you how to do part A. Started talking about B, but I'm going to back up and start sort of B all over again. So we had the 23 kilogram block. In the previous video, we found the FGY and the FGX. The FGY was 170.11, and the FGX was 147.88 newtons. Okay. This block has an FGY, so 170. It also had our normal force of also 170.11 newtons. Okay, gravity hasn't changed, so gravity is still pulling this block down the ramp. That's supposed to be just purely horizontal, of 147.88. That's not a comma, that's a decimal. FGX of 147.88 newtons, but because it's moving, it's a kinetic friction force. So our kinetic friction force, FFK, which equals mu k times the normal force, is found by 0.32 times the 170.11, which was 54.43, or 54 when you round, 0.44 newtons. So our FFK on our free body diagram, 54.44 newtons. Alright, so to determine what the acceleration is, our go-to equation is net force equals mass times our acceleration, but our net force is our total left, or sorry, our total right minus our total left. Our total right force is 54.44. We only have the one friction. And because the applied force goes away, that means there's only one force acting to the left, 147.88. And then that equals the mass. The mass is 23 kilograms. We got that. Times our acceleration. Our acceleration is unknown, what we're looking for. So 54.44 minus 147.88 is negative 93.44. Negative 93.44 newtons. That is the amount of our unbalanced force. Equals 23 kilograms times A. Divide by 23. You get 4.06, negative 4.06 meters per second squared, or 4.06 meters per second squared dtr down the ramp. Perfect. All right, moving on to question 3. So question 3 says, it's a discuss problem. It's not really a solve anything. Discuss in detail what the implications are if the coefficient of kinetic friction on a surface was higher than the coefficient of static friction. So, this first question, I feel like I'm missing a piece of this. I am missing a piece of that. Oh well. So, discuss in detail what the implications are if the coefficient of kinetic friction was higher. What that means is, in real life, usually, mu s, our static friction coefficient, is greater than or sometimes equal to our kinetic friction. What this is saying is flip it. It's saying that mu k is greater than mu s. What this one gives us, this is real, and this is what the question's asking. So what this says is that it's easier to push and keep it moving, whatever it is, keep it something moving, than it is to start it moving. Flipping this around is saying that it's easier to start something moving than it is to keep it moving. So this is what the question's asking. What that means is, in terms of movement, it would be much more efficient to move in jumps. We would move by having a kick, we would stop, wait for it, have a kick, stop, wait for it. This would be our most efficient way of moving. In our world, we start and just keep going. In the real world, we start and keep going because it's more efficient to do so. In the other world, it would be more efficient to give it a kick, wait for it to stop, give it another kick, wait for it to stop, give it another kick. This is the more efficient way in the fake world. Basically, what this question's asking is, it's a deeper understanding of if you truly can explain what coefficients mean and why they are. So, hopefully that helps. By kicking and getting it easier to start something moving than it is to keep it moving, constant pushes is a very different way of looking at the world. Think of being in your car. Instead of just pressing on the accelerator, you press it for a second, stop, wait for the friction to stop, press, stop, press, stop. It's a much more jerky world than what it is in our real world. So, explain why there can't be a negative coefficient of friction, whether it's mu s or mu k. Well, that piece comes about from the fact that our minimum coefficient is 0. And when mu is 0, no matter whether it's mu k or mu s, then the force of friction equals 0. So negative numbers, any negative number, is obviously less than 0. So that's saying that we could possibly have a less than 0 friction. But it doesn't make sense to have a less than 0 friction. That would just be something that doesn't make sense. Because how can you have less than 0 of something slowing it down? It would just be like a weird automatic speeding up of something. Somehow there would be an an extra force, the force of friction. Instead of slowing things down, it would actually be speeding things up. So when mu is 0, coming over here, when mu is less than 0, it means friction would speed things up, not slow them down. And obviously that would not be good for living because we would never be able to stop. Friction is one of the only things, it's the most common thing we use to slow ourselves down. I think the third question says, how would the world be different if our coefficients were usually greater than 1? So I'm pretty sure that's what it was. So if mu is greater than 1, how would that change our world? And that would change our world because that's saying that the force of friction, which is mu times the normal force, this is how much force to lift something. This is how much force it is required to push something. So if mu is greater than 1, then the force of friction will always be greater than the normal force. If that's true, then rather than pushing a car or whatever, it would always be easier to lift things rather than push them. But we know that in our world, it's much easier pushing them. It's much easier to push something than it is to lift it up, move it, drop it. In a world where mu is always greater than 1, it would be much more to move a hockey puck. It would be we would have to lift it up off the ground, physically move it over, then drop it back down onto the ice or whatever the case is. If we try to slide it, it's going to take a lot more effort, and for the same amount of effort, we might only get the puck to here as opposed to here. So having a coefficient of friction always greater than 1 means we have to do much more vertical motion. Well, rather than side to side, our cars would basically have to have pogo sticks jumping from piece to piece to break that friction. So hopefully that helps. All right, the last screencast we'll do question number 4.